Okay, so in this session, I'm gonna solve three more examples on the application of the linear momentum equation to find forces in different kind of hydraulic structures. So the first example I'm gonna solve is as follows. So we have this band here, and then we want to calculate, so the question asks us to calculate the horizontal which is in the x and y direction, right, in this plane, components of the anchoring forces or anchoring force required to hold the bend in place. Okay, so we have this band. The velocity at the entrance here is one of the fluid is 50 meters per second. We have the same velocity as it goes out. The P at the section 2 is 101 kilopascal, but the P at the section 1 is 150 kilopascal. And these are absolute pressure, so these are not the gauge pressure. And also the atmospheric pressure is given as 101 pascal, which as you see equals to the pressure at section 2. Okay, so we have a high pressure fluid that is coming from in section 1, and then a lower pressure fluid that comes out of the bend. And so we want to see what does this difference in pressure imply in terms of the anchoring forces that are applied to this bend here. Okay, so let's get started. So let me bring this down a little bit. Everything down. Okay. So the first thing I want to do is, answer, to draw the free body diagram of this bed. Okay, so this is the first thing I will do. So we have this bend. Okay, and then I want to draw the forces acting on this control volume of a of this kind of bend. So the control volume so the first thing again as you need to do is to first you need to select the control volume in this kind of problem. So this is the control volume I've selected. Okay, and you should select the control volume such that you have the information from the problem. For example, here we have V at section 1 here, and also a P and V at section 2. So that's why I selected such a control volume here. And then I plot the forces that act on this control volume. Okay, so first of all is Fx, F in the, so we have this coordinate system here. So based on that, I write the names of the forces. So we have Fy in the y direction. The second one is in the z direction or vertical direction, which I call that Fz. And then I have F in the x direction, which I call it as Fx. Also, we have the forces. So these are the forces acting on the CV contents. So the other forces we have are the fluid forces. So we have the pressure here. So let me show it with another color. So the pressure force acting on this CV is P1, which is the pressure, times A1, which will give me the force. And then the same thing here, we have another pressure, P2 times A2, which is also giving us the force that is acted on this CV. So again, these are forces acting on the CV contents. And to write it again, this is my show it again here. This is my coordinate system. Let me change it a little bit. So this is my coordinate system. I want to plot it again. And then the velocity components are shown with, in the y we show it with v, in the x we show the velocity component as u, and in the z direction we show that with w. So this is just velocity components in different directions. So we have v1 here that is going into the fluid, into this controlled volume, and then we have v2, the fluid that is coming out of this controlled volume. Okay, so this is the kind of free body diagram on this CV that I selected. And now this is the first step you do. And after you draw the free body diagram on a selected CV, a control volume, then you can write the momentum equation, okay? So, and then I want first write it in the x direction. So in the x direction, I have the momentum equation, and because I have steady flow, as it was not mentioned in the problem that I have any unsteadiness, so I can assume I have a steady flow. So for a steady flow, I can write this. Let's see the momentum equation for a steady flow. So this means that this term should be 0, and I'm going to only have these terms, right? So I just write it down. Let me see, copy. This is the term from the linear momentum equation. And because I'm in the x direction, so the first term is going to be u. So it's going to be the integral of over the control surface of u rho v dot n dA equals to the sum of the forces in the x direction. So remember, x direction is in this direction, right? In this direction, this is the x direction. And because u is 0 at section 1 and also section 2, this gives me, because you see here, right, the only places you have the fluid that is coming or out of the, going into or out of the fluid, the control volume is where is here and here. But u, which is the velocity in the x direction, is 0 here, right? We don't have any velocity in this direction, and the whole velocity is in the y direction, correct? So because u is 0, then this integral is going to be 0, and so fx is what? The horizontal force that acts in the x direction on this bend is going to be 0, the net force. Okay, so this is the first thing we can get from the momentum equation. And then the y direction, in the y direction, we have again the integral over the contour surface, and now instead of a u, I should write down v here. So v, rho v dot n. Remember, this v is the whole velocity vector. So this velocity vector is u I, again I write it down, plus v j plus w k. Okay, let me correct it a little bit. So this is small v, okay, this is small v, and the other one is capital V, the vector. Okay, v dot n dA, which equals to what? Which equals to the sum of the forces that act in the y direction, right? So what are the sum of the forces that act on the y direction? So it's going to be first Fy, which is here, plus I have these P1A, this is the first force that I have, P1A1, plus the second force, which is the pressure at section 2, which is going to be P2A2, right? So this is the sum of the forces. And then let's evaluate this one. So the way I'm going to evaluate it is as follows. So we have v at 1. So you see here the velocity vector, this is inflow, right? So we have to have a negative sign, right? And then this is outflow that is going out of that. So if I wanna again show the n vector, the normal vector, this is the normal vector to this. So these two have opposite signs, but these two, v and v2 and n, have the same sign. So for at section 2 we have an outflow, and the sign of that should be positive, and at section 1 we have an inflow, which means the flow is going into the control volume, so we should have a negative sign. Okay, so let me now write this down. So we have v1 minus V1, which is kind of inflow, rho A1 V1, okay, and then we have plus what? Plus V2, but V2 is in the negative direction, right? So here I'm gonna use, and this is because the first minus is because of the inflow, right? Because V dot n, this V dot n is gonna be negative here. V1 dot n is gonna be negative, so that's why we had V1 minus the whole thing, right? And then the second one is because we have V2, but V2 is in the negative direction, so the second V2 is because of the negative sign of V2, which is here. And then I have to multiply that by rho A2 V2. Okay, let me explain this again so you better understand what this comes from. Okay, so the first one, we have the first term of this is what is V, right? So V at V1 has a positive direction, so I'm gonna just write it as V1, right? Let me write it down here, plus V1. And then the second term, which is rho V dot n, how am I gonna evaluate that? So the rho is constant, so I just write it down. And V dot n, so V1 dot n, what is n here? N is in this direction, right? So they have an opposite sign. So V1 dot n should be negative. And I said again that because this is an inflow, V dot n should be negative for this one, okay? So here I have a negative sign here. So V dot n is gonna be minus V1 times dA, which is gonna be A1, right? So this is multiplied, right? So let me show it again. Perhaps I can do it like this, rho, and then minus V1 A1, okay? So this is how you get it. You have to be careful about these signs because they are pretty important. And then the second term, so we have first I want to write V here, and because V is in the negative direction, as you see it here, I write minus V2. And then because V2 dot n, which is this term, when I write it down, n is in the positive direction, and this is an outflow, so this has to be positive, okay? So again, this I write it as V2A2, V2 A2. Okay, so these are these terms equals to Fy plus P1 A1 plus P2 A2. Okay. So now I want to write continuity equation. Okay. And what was the continuity equation? If you remember it from previous lectures, it was the mass flow rate should be constant, right? That was what we had in continuity, okay? So now I want to use a way that we kind of derived it, and I want to use a form of that would be simpler for you to understand, okay? So let me see. If you remember from the continuity equation, let me go in the previous lectures. Yes. This is a continuity equation, right? Rho v dot n, I can write it as m dot, or another way of that is this equation we had, right? The mass flow rate. So let me write it down. I want to simplify my equation, so that's why I want to write this down. So rho AV or rho Q is discharge, right? So rho AV or Q shows the mass flow rate, right? Again, I can show it here again what we learned before. Here you have these, just as a reminder, m dot, the mass flow rate, you can say it's going to be rho volume instead of mass dot, which if rho is constant, you can just say it's going to be rho v dot, right? And then instead of volume, you can write ax dot, and instead of, and if a is constant, for example, for this problem that we have here, the a is not changing, you can take it out of the derivative, so it's going to be rho a times dx over dt, which equals to v. So this equals to rho av for a kind of fluid that has a constant a, right? So this rho av is nothing rather than the mass flow rate, right? So I want to just write it down again in this way. So this is another way because it's going to make it easier for you to understand. So these rho AVs that I have here are just mass flow rates, okay? And so as you see from continuity, it states that the mass flow rate that is coming into this control volume and goes out of that should be constant and should be equal, right? In other words, whatever comes into this control volume should go out of that, right? Unless you have a leakage, right? Assuming that there is no leakage here, right? So this is what I can say from continuity, and so write an additional equation here. So I just write it down. So m dot, the mass flow rate, equals to m dot 1, which is the flow in, and this equals to m dot at section 2, which is flow out, right? For these two sections. I can write this down. And so here, instead of rho v1a1, what I can write is, here I can write this as minus, this is minus m dot 1, and this is m dot 2, and because m dot 1 and m dot are equal based on this equation that I've written here, I can just factor m dot out and then write that equation as m dot minus m dot v1 plus v2 equals to fy plus p1a1 plus p2a2. Okay. So now I can. The question wants me to find the anchoring force required to hold the bend, and fx I found is 0, and now I want to find fy in the y direction. So fy is gonna be what? Fy is gonna be minus m dot v1 plus v2 minus p1a1 minus p2a2. Okay. So let's calculate what is m dot. M dot is rho 1 a1 v1, which is equal to rho 2 a2 v2. What is v1? V1 is 50 meter per second. A is constant here, which is 0.1 meter square. And rho, I can assume we have water here, right? So we have water, which is going to be 1,000 kilogram per meter cube. So if you want to calculate it, this is going to give us 1,000 kilogram per meter cube times A1, which is 0.1 meter square, times V1, which is 50 meter per second, equals to 5,000 kilogram per second. So this is the mass flow rate. You see that? You see the unit here? What does the unit show? Unit shows kilogram per second. That means how much mass is going per second, right? This is the flow rate, mass flow rate. Okay, so Fy now is gonna be minus 5,000 kilogram per second times V1 plus V2, which is what? We have it here, right? In this, it's gonna be 50 meters per second plus 50 meter per second minus P1A1. What is P1? P1 is given as 150 kilopascal, and P2 is given as 101 kilopascal, right? So I have all of that as well. So it's gonna be minus P1A1 and we have, these are actually absolute pressures, so you have to be careful about that, that are given to us. So let me see it a little bit. So I want to write this, I can write this in terms of the absolute pressure or in terms of the gauge pressure, right? So it's up to you how you wanna write it down, okay? So if we want to write this in terms of gauge pressure, we have to subtract P1 from 101 kilopascal, okay? So let's say, and we have, this is, we usually neglect the atmospheric pressure, right, in our calculations, because that pressure is always exist everywhere, so we always feel that pressure and we don't want to calculate it again. So we want to see what are the additional forces that act on that for example, this bend, right? But the but here we have the absolute pressure. So in order to calculate it, to calculate the gauge pressure, which is going to be the additional pressure, we have to subtract these pressures from the atmospheric pressure, which is 101 kilopascal. The same thing applies here. We have the atmosphere. We have the absolute pressure, which is 101 kilopascal. So we have to subtract it from the atmospheric pressure, and as you see here, it's going to be just 0. So I'm going to do that now. So we have minus 150 kilopascal, which is, this is the P1 absolute. I write it as absolute. And then we have 101 kilopascal, which is P atmospheric pressure. So this is going to give me, and times A1, which is 0.1 meter square. So the whole thing is going to give me P1 gauge pressure, right? And this is what we want here. And in these calculations for forces, we want to have the gauge pressure minus the second one. P2 is what? P2 is 101 kilopascal. So I write it down, 101 kilopascal minus, again, the atmospheric pressure, which is 101 kilopascal. Okay, times 0.1 meter square. So again, this is P2 absolute pressure. This is P atmospheric pressure. And the whole thing is going to give me P2 gauge pressure. Okay. And as you see, this is just 0, right? So if I calculate this, this is going to give me minus 500 kilonewton minus the pressure, additional pressure is going to exert 4.9 kilonewton, and the whole thing is going to give me minus 5 minus 504.9 kilonewton. So this is the force that is applied to this, that is needed for, required to hold the band in place, right? So in other words, this pressure, which has this pressure, which has a pressure which is higher than the atmospheric pressure, is gonna kind of have a force, give me a force in this direction, right? And then also the fluid that is going into this high speed fluid, also we need to have some forces to be able to kind of keep this kind of bend here, because it's a high speed fluid that is going in to this bend, right? So for example, it goes here and then it comes, and it kind of we have to change, it changes, this bend kind of leads this fluid to change its direction. So in general, this problem, we will have 504 Newton, which is in this direction, is the negative y direction that we assume, that needs to be applied to kind of hold this band in place, right? Okay. And again, so we have only a force in the y direction, and the force in the x direction is 0, which is, we found it here, right? So we will not have any force in the x direction, so it's going to be only in the y direction. Okay, so this is how the general framework, how you should approach these kind of problems. You just write the first the linear momentum equation, and most of the times, again, these problems are steady, so the first term is 0, and you only need to write the term which involves the calculating the kind of mass flow rates over the calculating the mass flow rates over the control surfaces. Okay, so and then you write the continuity equation, of course. You can write the continuity equation. Sometimes you may need to write other equations to be able to find these the final force that is needed for this problem. Okay, so now let me solve another example. So in this example, we want to determine the frictional force exerted by the pipe wall on the airflow between sections 1 and 2. Okay, what is this? So we have this pipe flow. So we have this pipe. Again, let me see. Okay, so we have this pipe. This is our coordinate system, x and y. And then we have two sections here. So section 1 is gonna be here. Section 1 is here. T1 is 540. We have air. And P1 is 100 psi. And we have section 2 here. T2 is 453. And we have V2 here. V2 is also given, which is 1000 foot per second. So the configuration of this problem is similar to one of the previous problems. Let me write this down. So we have T2 And then we have P2, which is 18.4 psi. And also the V2 is also given here. So we have V2, which is given as 1000 foot per second. And we have V1 here. Which is not given, okay? So the question wants us to find the frictional forces that is exerted by the pipe wall on the airflow between this section 1 and 2, okay, in this problem. So, what should we do? We don't know V1, and we have to again use the linear momentum equation, okay? So this is what we have to use. But before using that, we have to know V1, okay? And for finding V1, because we have a pipe flow, we can use continuity equation, okay? So answer. But this problem, if you remember this, so we have to find, we first need to find V1 from continuity equation. So from previous example in class, so if you remember, we had this problem before. Let me show you in the continuity equation, right? This is the problem, right? So from this example, you can see that we found velocity at section 1 using the ideal gas law and continuity as 219 foot per second. Okay, so it's the same problem. I can write continuity plus ideal gas law is going to give me V1 equals to 219 foot per second. Okay, so this is the first part of the problem. And now for the second part, we want to find the force, that the frictional force that is exerted by the pipe flow on by the pipe wall on this airflow between sections 1 and 2. Okay, so this next thing I need to do is to draw a control volume between these two sections, right? So that is the first thing I need to do. I draw a control volume, and then I want a control volume that contains both section 1 and 2. So this is going to be my control volume. So this is the CV. And now I have to draw the free body diagram, the forces that act on this control volume. So what are the forces that act on this? First one is pressure at point 1, which is this P1, A1, at section 1. And then we have the pressure at section 2, which is going to be this, right? P2, A2. And then we have all these frictional forces, the small frictional forces that act on the pipe wall. So instead of all of those, I can write the sum of all those forces as Rx. I'm going to just show that as Rx. So Rx is going to be the resultant force. Or let me write it down here. Resultant. Let me just write it as the sum of all frictional forces. Or net frictional force. Let's say it is net total frictional force. Okay. So now again, because this is a steady flow, I can just write this formula here. It's in the x direction. Copy. This is in the x direction. Let me copy that. So we have a steady flow, so I can write this down. And so now we have the sum of the forces in the x direction, which are going to be what? Which is going to be first minus Rx, which is the resultant frictional force, plus P1A1, which is in the positive direction, minus P2A2, which is in the negative direction of x, right? And again, there is for this formula, for this integral, there are some easier ways for you to remember that. So maybe this integral is a little bit harder, but after you solve some examples, you can come up with a simpler form of that, which is just m dot times v, right? You just, instead of that, this is going to be the mass flow rate times the direction. So what you need to do is you say, okay, do I have a mass inflow or outflow? Right? So first of all, you have to write the direction of V1, right? So I have U1, which is in the positive direction. So I write it as U1 plus U1. And then I have to multiply that by the mass flow rate. So is it inflow or outflow? The mass flow. Is it going into the control volume or is it going out of the control volume? As you see, the mass is going into the control volume. So I have to have a negative sign times the mass flow, which is mass flow rate at 0.1, right? So it's going to be minus m dot 1 plus the second part, which is the integral over this control surface, which is going to be u2. Is it in the positive direction or negative direction? It's in the positive direction. So I just write it as the sign of that is going to be plus u2. And then m dot 2, the mass flow rate at section 2. The flow is going out or is going into the control volume? It's going out of the control volume. So it should have a positive sign. So I'm going to write it as m dot 2 plus m dot 2. And this is how you can write this integral, right? So if you can't remember this integral, this is nothing rather than u at that direction times m dot at that section, right? So the inflow, the mass flow rate, right? Or another way you can show that. So let me write this down here. So you can either remember it as this, the linear momentum equation as this, or another way you can remember it if you want to include other terms. You can remember it as the one we wrote here, which is V1 times rho AV, rho VA, right? So you can remember it as U times rho AV, right? Rho AV. Or you can even remember it as U times rho QV, rho Q, U times rho Q, or rho QV. This is another way. So these are different forms that you can remember this equation, right? So let me write it down here. So instead of this integral, if it is hard for you to write it every time and calculate it every time, these are alternate forms that I suggest you to remember one of these at least. So rho QV, you can even say rho QV at, for example, Q1, V1. This is Q1, U1, A1 at that section, right? Or section 2. So you can calculate this like this. And just you need to be careful about the kind of signs, right? So I think this one is the easiest form, but some people are more comfortable like with rho QV in the volume flow rate when you write it down like that instead of mass flow rate. Because some people are more comfortable with this form, U times the mass flow rate. And so these are different forms you can write it down, but let me write this alternate form of linear momentum equation. Okay. So this is just a side note. So this again, and now we have this equals to minus Rx plus P1 A1 minus P2 A2. And from continuity, we can write m dot equals to m dot 1 equals to m dot equals to m dot 2. This is from continuity. And we know A1 equals to A2, right? We have it here. So I can factor m dot out here and write m dot U2 minus U1 equals to minus Rx plus A2 P1 minus P2. Okay? And the unknown here is Rx. So I just write it down. Rx, which equals to A2 P1 minus P2 minus m dot U2 minus U1. Okay. So I don't have rho here. So I need to use, I don't have m dot, so I want to find m dot, right? And for m dot, I need to have rho AV, right? So m dot equals to rho AV. And A2 is what? A2 is PD2 square. So A2 is PD2 square over 4 if this is circle, cylinder. And m dot is what? It is rho 2 A2 U2. I can write this as this. But I don't know rho 2, right? Rho 2 is not given to me. But I have all these other things, so I can use the ideal gas law or equation of state. So rho 2 equals to P2 over RT2. This is equation of state. So I just write it down here instead. P2 over RT2 times A2, which is PD2 square, pi D2 square over 4 times U2. Okay. So R is the constant, the gas constant is 53.3 foot-pound and so if you just now put everything back into here in this problem, and D, I think D2 I had to write it down, but this is from the other problem, so this is just D1 equals to D2 equals to 4 inch. If you just plug all the numbers into this equation, this gives me m dot equals to 9.57 pound mass over second. And if you substitute that into here, we get Rx equals to, the first term is going to be 1025 pound and the second one is going to be 232 pound, which in turn is going to give me 793 pounds. So this is the frictional force that acts on this airflow that is moving along this pipe, right? And again, the main strategy here that you need to use is first drawing a control volume. That is the main important thing. So for this kind of problem is easy, but sometimes it becomes challenging if the geometry of the problem is more complicated. But in general, you need to draw a control volume that kind of makes your problem easier and includes all the information that is given in the problem. And then you draw the free body diagram of the forces that act on this control volume. And then you write the linear momentum equation. These are alternate forms of that if you don't remember, and I suggest you remember this one, U times m dot, in this form that we have shown here. And then this equals to the sum of the forces that act on the that control volume. And then you should also write, you can also write continuity equation if you don't have enough you have more unknowns. Another equation that you can write is continuity equation, and combining these two and other equations, like if you have an airflow, usually you need to write, if you have like, if temperature or pressure is given to you, you usually need to write equation of state to find the pressure or density, and then substituting all of these will give you the total force that acts on that control volume. Okay, so in the next part, I'm going to solve another example of this linear momentum equation.